Fun story. On my first take doing question D here, I entered the wrong thing in the calculator somehow and made a terrible mess, and I didn't want to lose all my work, so I started a new video where I will hopefully be a smarter man. So, D is a different structured question because they give you the H3O concentration. So we start with our formula that says H3O equals root Ka times HA. But instead of having us find H3O like before, they hand it to us. They say the H3O is right here, 1.114 times 10 to the minus 5 moles per liter. And that equals the square root of, we need the acid constant for hydrocyanic acid, which is in the book. It's 6.2 times 10 to the minus 10. And that's times the acid concentration. I'm just going to use the letter A for that instead of writing the brackety HCN thing. This is easier to read. So we want to solve this for A. Get A by itself. First problem, the A is under a square root. So to strip that off, what's the opposite of square root? Squaring. If we square both sides of this, like so, on the right side, the square and the square root will kill each other. And on the left, we get a calculation we have to do. 1.114 times 10 to the minus 5 squared gives 1.241 times 10 to the minus 10. And that equals 6.2 times 10 to the minus 10 times the acid concentration. Okay, now, if we want A alone, the trouble is A is multiplied by 6.2 times 10 to the minus 10. What's the opposite of multiplying by 6.2, blah, blah, blah? Divide by it. If we do that, we must do the same thing on the other side of the equation, because that's how algebra works. Sorry, getting illegibly small. The jerk who designed this workbook didn't leave a lot of space for these. It was me, sorry. So, number on the left side divided by 6.2 times 10 to the minus 10, and we get 0.20 moles per liter. Only two significant digits because that's usually what happens when you invoke an acid constant. Okay, what else can they do to us here? A solution of hydrofluoric acid, same thing actually. They give us the H3O here and ask us to find the acid concentration. So the H3O is 0.021. That equals root. The acid constant for hydrofluoric acid is 6.3 times 10 to the minus 4. Times, I'll use A again, it worked last time. Okay, so again, if we want A by itself, we square both sides first. 0.021 squared is 0.000441. And because we squared this side, which gave us 0.000441. We square the right side, which just strips off the square root. So now we have 6.3 times 10 to the negative 4 times A. We want A alone, so divide both sides by 6.3 times 10 to the minus 4. And we get A equals 0.7. Remember, that's a concentration, so it gets units. You're kind of wrong if you give an answer without units. Not too bad, I hope. Let's see if we can get through one more. We have, okay. Another different kind of question they can ask. Let me just set up our formula again. H3O equals root Ka times HA. Okay, so generally when we use this, we're trying to find an H3O concentration. And we've seen that sometimes they tell us the H3O and ask us how much acid there was. This new one is they're telling us the H3O concentration. It's 0.004266 equals root. Now in this question, we don't know what our acid is. We just have a bottle of mystery liquid or a sample of mystery liquid. It has this H3O concentration, and they tell us its concentration for the acid is 0.2. But because we don't know what acid it is, we don't know the Ka. Well, neat trick. If you know both of these numbers, we could solve for the Ka. Let's see if that gets us anything. If we want to solve for Ka here, as before, our Ka is trapped under a square root, so squaring both sides will help us. If we do that, the square and the square root annihilate each other, and we get 0.004266 squared is 0.00000182 equals the acid constant times 0.2. Should I have written this in scientific notation? Yeah, probably. If you want to do 1.82 times 10 to the minus 5, you're a better person than I am. I, I just think this is more readable and maybe more comfortable for some people, so I'm going to go with this. But if you're happy going to scientific, bless your heart, you'll do fine. If we want Ka alone here, we have to get rid of this 0.2, so the opposite of multiplying by 0.2 is we divide by 0.2. Are these zeros on the end necessary? No, not really. Okay, so we take our left-hand number divided by 0.2, and we get Ka is 0.000090994 according to my calculator. If I take that to scientific notation, 9.1 times 10 to the minus 1, 2, 3, 4, 5. Okay, so if we know the acid constant, we can go to the acid-base table and scan the acid constants and see if you can find an acid whose Ka is 9.1 times 10 to the minus 5. It looks to me at the very bottom of the top page, page 8, ascorbic acid, also known as vitamin C, has exactly this Ka. So if you can find the right numbers for an acid, you can actually identify what acid it might be. This isn't a guarantee. There are probably other acids that have this acid constant, but if you were reasonably sure this was vitamin C, or if you had a short list of acids that this could be, this is good evidence that your sample is made of vitamin C, ascorbic acid. Good. I wish we could say we were done with the math. We are not, but hold strong. I'll be there with you. See you in the next one.